Hey everybody, welcome back to the newest unit in our class. We're going to get into a thing called rational expressions, and we're going to learn all about how they work and how they operate, and that will be this unit. And eventually we're going to get into graphing them and learning all sorts of neat stuff. But we're going to start with kind of what they are and how they would look as a function. And then we'll start talking about domain restrictions, okay? And then we'll start playing around with them as we go along. So we'll get into, of course, you know me, we'll get into vocabulary real quick. We have to make sure before we go into a rational expression, what is a rational number? And if you recall from all sorts of history of math, you've seen this before, I hope, is any number that can be expressed as a fraction. Okay, so if it can be expressed as a fraction, it is a rational number. All right, so it takes the form of, we normally call it A over B, where B is not 0. Okay, so that's going to be important in a second. Okay, so a rational number is any number that can be expressed as a fraction, A over B, where B is not 0. And so we can get into all sorts of neat-looking algebra things that fit this description, and we have to recall this special rule where B is not 0. And we look at the first problem in the notes that I'm going to present you with. State the domain of the following function, 1 over x, or f of x is equal to 1 over x. And so we have to go back to the guaranteed pass notes from the very beginning of the year, and we talked about parent functions and what they might look like. And if you recall those guaranteed pass notes, when we were graphing this, something's going to pop up. You know how we graph, we make our XY table, we make our numbers for x, and we figure out what we can get for y, and we know that if x is negative 2, y is negative 1/2. If x is negative 1, y is negative 1. If x is 1, y is 1. If x is 2, y is 2. And you're thinking, or y is 1/2. You're thinking, Mr. Katz, wait a minute. Hey, buddy, you skipped 0. I did skip 0 because that's going to be the main point of this lesson. So I skipped 0. Why? Well, if you recall from the guaranteed pass notes, when we would substitute 0, we would have 1 over 0. And if you remember, that was undefined. So 0 was undefined. And it goes back to this definition where b is not 0. Okay, so we have a rational number is any number that can be expressed as a fraction where b is not 0. And that leads to another vocabulary term that we have talked about, again, previously, called a domain restriction. Okay, so it's called a domain restriction. It's any value that the domain can't have, right? Or any value for the variable that can't be presented in the domain. So in this case, a domain restriction is basically anything that can't happen numerically, anything that would cause an undefined result. Okay, so anything causing an undefined result creates a domain restriction. So we got to know this vocabulary. All right. So in the example of question 1, clearly we see that the domain restriction here is that x can't be 0. And so what we're saying in problem number 1 for the domain is that we're saying x cannot equal 0. All right, so x cannot equal 0. Now, because I am me, and you know me, I'm not the nicest guy in the world. Since I am me, I'm going to ask you to report this restriction in something called set builder notation. Okay, so we're going to report this restriction in something called set builder notation. And so we have to know some more vocabulary. So what is set builder notation? It is more complicated than how it sounds. So I'm going to give you an example. When we wrote x cannot equal 0, this is what it looks like in set builder notation. This is a hoot. I love it because it's so unnecessarily complicated. So it's a hoot, right? You look at this notation, and it's got all these symbols and crazy stuff. But when you look at this notation, what are we saying? We're saying this: x can't equal 0. So it's set builder notation. You need your brackets, okay? Need the brackets. Need these. And then we have this little thing, whatever this is. Okay, we're actually saying for all x's, okay? Okay, so for x, right? For x, that's part of the set builder notation. And then, well, x is the actual restriction here. In this case, x can't equal 0. Okay, so the actual restriction. So you may see set builder notation that takes all sorts of crazy shapes and forms and all that stuff, and you'll see as we go across this lesson how set builder notation looks. But I am going to, unfortunately, expect you to put things in set builder notation, because you have to get used to the symbols that are out there, because it's almost like coding. Not everyone that's watching this is going to be a computer programmer, but maybe some of you are. And so this is going to be kind of like, it'll help you with that same type of process to read symbols in a different way and know what they mean. So when we look at the problem in number 1, we have that function notation. A rational number is where the denominator can't equal 0. Okay, so anything causing an undefined result. In this particular case, the denominator equaling 0. And hopefully I say that now, and some stuff from the previous unit starts to come back to you. Okay, so a domain restriction, anything causing an undefined result, the denominator equals 0. When we get into radical expressions, there'll be some more stuff. All right. So anyway, that's the concept. I'm building the notes around the first example. Okay, so remember the directions. We're going to state the domain of the following function using set builder notation. We start with this function, the first function, 1 over x. X couldn't be 0 because we can't have 0 in the denominator. So all we have to do is state that using set builder notation. X can't equal 0. And that's it for the notes. The rest is practice. So now we take a look at this this function in problem number 2. All right, so what is this all about, right? So remember what the domain restriction means. It's anything that would cause an undefined result. And when we look at this crazy-looking polynomial with a fraction, okay, this crazy-looking polynomial with a fraction, we have to look for anything that would make the denominator 0. Is there any possibility of the denominator equaling 0? Okay, and when you think about looking at this particular denominator, this particular expression, you might think, well, there's no variable down there. So you look at this expression, there's no variable down there, so there's actually no chance. There's no chance of the denominator equaling 0. All right, so is there any possibility of the denominator equaling 0? No chance. Nope, no chance for that to happen. So what does that mean? That means there is no domain restriction, okay? So there is no domain restriction. So the domain could be anything at once, which is funny. So there is no domain restriction. The domain can be anything at once, but here we go. We have to express that in set builder notation. Okay, so in set builder notation, remember, we're going to need the brackets. We're going to need the x. We're going to need that line there. Okay, that is set builder notation. And all this is saying is for x, or for the variable x, what can x be, or what can't x be. And so we'll say for all x, x is all real numbers. Or we can just say all real numbers. There is no restriction. Okay, so for x, x is all real numbers. Or we can just say all real numbers. Okay, so either way, it's set builder notation. You want to get used to kind of how it looks. You get the brackets, you're defining for x, and then you're stating what x can or cannot be. And then from there, it's really a matter of taste and choice by whoever is assessing you. Some people are really, really hardcore when they say, well, you can't repeat the x there, or in the previous case, you have to write x as all real numbers except for 0. So it all depends on who's assessing you. Me, I'm a little bit more laid back when it comes to that. I just want you to get used to the format, and that'll help you. So in this particular case, there's nothing x can't be. Therefore, the domain is all real numbers. We have stated the domain in set builder notation. All right, so now we look at number 3. In number 3, we have an interesting rational expression. Okay, so here's number 3. We have an interesting rational expression. Now we have to think. Is there anything that could make the denominator 0? Okay, so we think, let's look at the denominator. Is there anything that could make the denominator 0? And so we're going to look and think, well, how will I find the answer? Why don't I just set the denominator equal to 0? So what if I set it equal to 0, and then I can figure that answer out? Okay, so let me set the denominator equal to 0, and I can figure this answer out. For this particular example, if I just solve this equation for x, I will find, well, x is 0. So is there any chance for the denominator to be 0? The answer is yes. If x was 0, the denominator would be 0. Okay? So if x was 0, the denominator would be 0, and that is our domain restriction. Okay? So that's our domain restriction. If x is 0, the denominator is 0, we have now found our restriction. So how are we going to list that in set builder notation? We need our bracket, we need our x, and our identifying line. And all we're saying is that x can't be 0. That's all we're saying, right? X can't be 0. So how will I write that? X cannot equal 0. Ta-da! Set builder notation. That is the domain restriction in the function for number 3. Okay, so that's how that's looking. So now we can look on to the next one. How about the next function in number 4? We had f of x is equal to 5x squared minus 3 over x minus 1. So we have this this funny looking expression. So we have to ask the same thing. What would be the domain? And the domain is there any possibility for the denominator to be 0? Okay, so is there any possibility for the denominator to be 0? And well, let's find out. How would we find that out? Set the denominator equal to 0. Okay, so here's a neat time to pause, right? Set the denominator equal to 0. And some of you might be saying, well, what about the numerator? And the answer to that question is, who cares about the numerator? There's nothing stopping the numerator at this time. Okay, don't worry about the numerator. That's a kind of a good note there. Don't worry about the numerator. Who cares about the numerator? We'll get there later because there's going to be some stuff in the numerator that can happen eventually. For now, because we'll get into radicals and all that stuff. But anyway, so is there any chance for the denominator to equal 0? And yes. If x was 1, the denominator would be 0. Okay, so if x was 1, the denominator is 0, so x cannot be 1. And if x cannot be 1, well, we can express that in set builder notation. Okay, so for all x's, x cannot equal 1. And like I said, some assessors will say, well, you have to write x as all real numbers except for 1. Use symbols. I'm cool with that as long as you have the right format. So that's it for number 4. Now we look at number 5, and things get a little bit nutty, right? So here we're looking at number 5, and I'm thinking, oh man, that looks so complicated. I don't know what to do. And I'm thinking, yeah, I bet you do. I bet you do know what to do because you guys were rock stars in that last unit. And if you weren't rock stars in that last unit, I strongly encourage you to go watch and listen to those videos again because you should be rock stars after that last unit. So with number 5, we get this crazy looking rational expression, right? And is there any chance for the denominator to be 0? Well, let's find out. How could we figure that out? Let's set the denominator equal to 0. And so what we're going to do is take this crazy old denominator and set it equal to 0. And I know you're thinking, well, what about the numerator? And again, who cares about the numerator? The numerator doesn't restrict the domain because there's nothing in the numerator that leads to a restriction yet at this point. Eventually we get there. And so now we have to solve this, and hopefully you're thinking, how will I solve this? And you go back to the previous unit and remember our good friend, the zero product property. If we have things being multiplied and the result is 0, we have logical conclusions that can be drawn. Okay, so either this thing is 0, or this thing is 0, or this thing is 0. Okay, so we have logical conclusions that we can draw. So the only problem is, how can we express this, this expression as a product? And that's where factoring comes in. Okay, so we're going to factor x squared minus 2x minus 5. And we can use mental math here, I think. So we set up our parentheses, and we think, what two numbers multiply to negative 15, but add to negative 2, and hopefully you're thinking negative 5 and positive 3. If we were to multiply those two things out, we would have our expression here. So we have factored that out. It's going to equal 0. So then what would be the solution? That means in this case, x would be 5 here, and x would be negative 3 here. Because if x were 5, it'd be 0. If x were negative 3, it'd be 0. Or just each one solve for x. And again, if that's a problem for you, pause here, go back to the previous unit on polynomial equations, and look for the video notes on solving polynomial equations. So we have our restriction. So basically, this is what we're saying. We're saying x can't be either of these. Okay, so x cannot be 5 or negative 3. And now we get into, well, how would that look in set builder notation? Okay, so set builder notation, we got our funky looking symbol. And, well, x cannot equal 5, and x cannot equal negative 3. So we use set builder notation to figure, okay, so for all the x's, there's our restriction. And that's how that works. So basically what we're doing, if you haven't caught on yet, what we're doing is set the denominator equal to 0. See what happens, right? All right, so on to the last one. Because I like this little trick. Last one has a little trick. So we have h of x is equal to x plus 4, x plus 2. Okay, x plus 4 over x squared plus 2, right? So we look at this rational expression. We're thinking, well, is there anything that the domain can't be? So we're going to do the same thing we've done the entire time. We're going to set the denominator equal to 0. And so we're going to have x squared plus 2 equaling 0. So, well, what do we do? How do we solve for x? Okay, so how do we solve for x? Let's isolate x. We're going to see something cool. And if we isolate x, we subtract 2 on both sides, right? And so we'd have x squared equaling negative 2. How would we solve for x now? We got to undo the second power. How do we undo the second power? The way we undo the second power is to take the square root of both sides, which is a hint into the next domain restriction that we will get into eventually, I hope. So when we take the square root of both sides, we know that x will be the square root of negative 2. And if you try punching that in your calculator, or you do a little thinking, guess what? That's undefined, so that's undefined. What just happened? So if this is undefined, what does that mean for the denominator? Okay, so what does this mean for the domain restriction? Okay, so now we have to keep our domain restriction. We have to keep our wits about us, right? What were we doing? What were we doing the entire time? The entire time we were doing is trying to figure out what the domain restriction was, right? So if this little equation to figure out what x could possibly be to make it 0 is undefined, what does that mean? That means there are no domain restrictions. There is no restriction on the domain. That means the domain can be any x it wants to be. So that means there are no restrictions, right? What? That's crazy. And so you look at this original thing, you see x's in the denominator, and of course you're thinking, dude, that's got to have some type of possible restriction, but nope, there isn't. Because there's no number that when you multiply it by itself will give you -2, right? No way. So there is no restriction. So what do we do with set builder notation? We set up our little thing and we say all real numbers. Okay, so for all x's, x could be all real numbers. So anything like that is good enough for me anyway for domain restrictions. Some assessors might be a little bit pickier, but if you get this, you can deal with whatever. If your teacher's really picky about one thing, you can just accommodate that. So I've set you up for success either way. So that is domain restriction. And how does that work? Well, do you even remember the guaranteed pass notes? I hope so. Because when we looked at this graph, do you guys remember what it looked like? It's a funny looking graph. So when we graphed this, how did it look, right? How did it look? Well, it looked like this. We had one part of it going this way, right? And the other part of it going this way. If you remember, that's what that graph looked like. And so we got these funny looking pictures now. Okay, so when we finish, we got to keep in mind, what did the graph look like? Kind of look like this. And notice if the domain restriction is at 0, here's 0 on the x, that the graph won't cross x, but that's for a later time. All right, that's enough. I've talked enough. I hope you got at least a good sense of what a rational function is and what a rational expression is and what a domain restriction is. We're going to build on vocabulary, and then we're going to operate with these bad boys later on. So take care. I'm out of here.